So let's start the total life. Okay, what's a cyclic loading is some kind of like loading is some kind of like sinusoidal curve, you know, like up and down, you know, like stress is increasing but decreasing, increasing and decreasing, something like that. Let's try to understand. Let's try to understand, you know, physically, like visually understand what happens in the material. So the y-axis is stress, some kind of like loadings, right? Loading divided by area is the stress, right? And then the x-axis is, maybe we can save it, time. Then what happens if you have the materials and then like boom, 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 boom? That is the cycling, right? Cyclic loadings, right? So we can divide it into certain period. And then some kind of loading could be like this. Up and down, up and down, up and down, and so on, right? However, sometimes like we can like make me like this kind of, can you hear guys, like can you hear my voice, right? Like these kind of things, but sometimes like it could be stronger, right? So which means that the amplitude can be changing. So maybe the loading condition is something like this. Boom, up, down, up, down, right? Even like much harder, like much stronger. It's up, down, up and down. This is the cyclic loading. You have your materials, you're heating the materials in some kind of like loading, like different stress. Sometimes it could be like tension, compression, which means that if the zero is here, then maybe the positive stress, negative stress, something like that. Then what happened in the like failures, in terms of failures? Okay, based on these kind of informations of your cyclic loadings, let's try to test how your cyclic loadings changing. I mean, the cycles could be changing. So x-axis represent the cycles, the number of cycles, and the y-axis representing the stress amplitude. What is a stress amplitude? Stress amplitude is this one, or this one, or this one, some kind of like amplitude, right? So as you can see here, the green one amplitude is much lower. The red one is a little medium, and then the blue one is much higher, right? And think about that. Which stress type will make the materials or device broken earlier? Definitely blue one, right? Because it's the magnitude of the stress is much higher than the green one, right? So, I mean, think about like at the very some, like for example, if you test it with these kind of forces, then okay, we have like when this cycles, it's broken. Okay, let's start maybe higher stress. Okay, it's broken earlier, right? Because this is the number of cycles. It's broken earlier. What about if you choose a lower magnitude of the stress? It's broken much later. Maybe here, maybe here, maybe here, maybe here, maybe here. So we check multiple times, right? However, if you choose these values, when it's break, I don't know, maybe some here. What about here? I don't know. Maybe here. What about here? I don't know. Maybe it's not broken because the stress is too low. What about here? Maybe something like here. So some researchers do multiples and numerous experiments to broke with some certain values of the stress amplitude. Then we can draw some kind of like stress versus cyclic number of cycles plots. And this is something like these kind of like exponent relationship could be expected, right? Okay, so let's remove this kind of dots. And then let's try to see more like arrange and then more idealize the curve. Something like this. This is more ideally. So when you actually have very, very low amplitude of the stress, which is the green one, maybe the number of cycles is very high. So maybe it's something like here, the green ones, cycles. And then this represent this kind of the amplitude because it's very low, correct? I will make it a little thinner. And the red one, maybe somewhere here. And it has like little lower, like a less number of cycles because the stress amplitude, it's higher, larger than the green one. What about the blue? Maybe it's broke earlier because the stress values is actually way larger. This is very like theoretical and ideal shape of the stress strain curve. Not the stress strain curve, like a stress and cyclic stress amplitude versus the cyclic number of cycles. But I think you can understand these kind of situations. Okay, you have a cyclic load, and then when you increase your amplitude of the stress, your kind of like number of cycles could be changing. Okay, this is the scale is just like a natural scale. However, as you can see, this is like many researchers did some kind of studies. They realized it's actually related in exponent style, exponent like relationship. So we can actually redraw this graph into the log scale, right? From this. So how we can change this graph into log scale, then how the graph gonna be changing. So I will draw on the bottom right here. Same draw. As I mentioned, like this relationship is the exponent. So when you actually change the logmetric scale, and what happened is something like this. So this is a SN plot on linear log scale. Okay, then you have to understand the values of here. So first, what's the intersections right here? The y-axis intersections that we can call the fracture stress. Because imagine that what this means. It means that the number of cycles is 1 because this is log scale. So number of cycles is 1. So in one time, you can break your materials, which means that your amplitude of the stress is corresponding to the fracture stress. So, and also, what is this? Why is this? Because this is exponent relationship. So when you convert into here, then this kind of like is very stiff. So we have a linear relationship up to here. But at certain point, it's just like plateau. Why? Because imagine that you're dealing metal, but like you're just barely touching. That like if you're cyclic loading more than like millions time or like millions of millions time, it will not broke. It's gonna be forever. So these values is gonna be like nothing changing, even though like 10 to 6 times, 10 to 7 times, whatever. So as I mentioned, if this value is like 10 to 6 or 10 to 7, whatever, at the certain values of stress amplitude right here, there's no changes in number of cycles. And that we call sigma E. And this is the endurance limit. Okay. And the endurance limit is here. So whenever you're cycling, like loading like more than like 10 to 6 times, 10 to 7 times, and 8 times, it will not be broken. So I think you understand this kind of cyclic loading situations, and I think you can easily like expect or imagine these kind of like situations of the materials, and then you change the scale to from the natural numbers, just a number, and from the numbers to the log scale, then it's going to be linear, and then it's going to be plateau. I think you understand this. Okay, then we can make these lines or graph into some mathematical way, and that way is the Basquine equation. So yeah, you're right. The one student asked me the sigma f. So that is your assumption. So the fracture stress, which is sigma f, could be the ultimate tensile stress, ultimate UTS, because it's assumptions. Like if you expect that, so when you actually approach the problem, I think it's highly related to your homework number 1. So you can actually say that this one is the sigma UTS, which is ultimate tensile stress, because this is your assumptions. And what this means, just one time it's broke. And what that means, that is the ultimate tensile stress, right? So it is your assumption. So basically, if you write your assumption, I will just say the sigma F is equals or similar to the ultimate tensile stress, then you can go for it. It totally makes sense. Okay, so let's go to the Basquine law. So if you try to express this kind of phenomena to some kind of mathematical way, that is the Basquine equation. Now we can say sigma A, which is stress amplitude, it equals to sigma F prime times 2 cycles times B, which is exponent. This is the Basquine equation. I know that like some textbook write this 2NF, 2 times NF, like it could be, I mean, sometimes like replaced with like NF, but I will explain later. But as far as I know, the form of the Basquine equation is this. And then what is the sigma A, as I mentioned? Stress amplitude. What's this? This is fracture stress or ultimate tensile stress, based on, it could be different by your assumptions, or it could be the yield stress. So usually like yield stress value could be like here, like little like higher than the values of the fracture stress, because like this one will not broke anymore. So that's why we can draw something like this. But anyway, we can say that this sigma F is equals to the ultimate tensile stress, whatever. So this could be determined by your material property. Material property. Okay, so now, as I mentioned, many researchers or unfortunate grad students like me do a multiple times of experiments, and then we test it 1 time, 2nd time, 3rd time, 4th time, many times, and we can get this kind of understanding of the linear relationship. So let's try to get the exponent of or variables such as B, or such as like cyclic cycles based on this relationship. Let's try to make a log here. So I know you do the little math here. So when you take the log sigma A is equals to log F times 2 NF times B. Okay, I think I need to tell this one. So some people say that this Basquine law, something like this. Okay, so this is the material's property, but sometimes because of these 2 cycles, they just make just the 1 cycles here, and then they just change the variables of exponents, something like a and b, instead of using this. So some Basquine law, like some people actually say that the Basquine law, rather than 2 times of nf, they just wrote the nf. So don't be confused. At this point, I will just derive without 2. I think you understand why, because if there's a 2, it's the derivation is a little hard, but you will understand it's not big difference. It's just matter of, it's just like calculations. So as I mentioned, originally the Basquine equation is amplitude is the material property times 2 cycles, but some people actually say it like this, but I will start the derivation from here. Then maybe we can switch the other based on the different sample problems. You will understand if you continue to listen. So since this is the now is not 2 times, so it's just a cyclic cycles. So this is right. And then if you take this log here, it's gonna be log this plus b times log cycles. I think you know that, right? Okay, then among this many points, let's choose something like this point, and let's choose something like here. Okay, just choose arbitrary like points. You can choose here and here. You can choose here and here. But I will just select these 2. Okay, no objections, right? These 2s. So let's say this one is 1. Let's say the other one is number 2. In this case, no matter what situation here, these number point dots should still matching with the this equation. So which means that I can insert this number, which is point A, which is 1. And then this sigma f is the materials property, so it's not changing, plus b times log cycles, which is 1, because the 1 cycles is here, and then the amplitude is here. Okay, what about the second point? The second point also should be in the Basquine law, Basquine equation, but the data point now is number 2 because I choose here. Here. So the cycles of 2 is here, and then amplitude is right here. Okay, then you have 2 equations, and you still don't know 2 variables, which is sigma f prime and the exponent b. So 2 unknown variables, 2 equations, then you can solve it. So I will just subtract these equation number 1 and 2. And what happened is, because sigma f prime is the material's own property, so it will be same. So it will be deleted each other. Then what happened is, amplitude 1 minus amplitude 2 is equals to b is same because it is the exponent of determined by the materials, and then log cycles of 1 minus log cycles of 2. Okay, and then you know this, you know this, you know this, you know this, you don't know this. Then now you can calculate the b. So the b is equals to amplitude 1 minus amplitude 2 over cycles 1 minus cycles 2. Super easy. This is the first equations or derivations that you have to start to solve the ascent curve problems, which is B. Before going to further, I mean, I have like very many problems after this, but let's try to mention. I want to mention of this. So this endurance limit is kind of reference or kind of like minimum stress amplitude, which will not broken in cyclic loadings, and this endurance limit could be affected by numerous sample preparation conditions or post-treatment of the materials. So it's very important for you to understand how we can increase or like how could be decreased by different setups or different conditions. So endurance limit, which is sigma E, could be affected by first surface finish or stress concentration, heat treatment, like annealing. What else? Environment, like no chemical attacks or no acid, something like that. Or maybe good component design. So you can increase your endurance limit based on these different considerations when you design some material devices. So you can increase the values of endurance limits, which means that you can make a better or more fatigue resistance of devices. Okay, so this is very important to understand. And for you guys, I will write more. So this sigma E is the endurance limit. Important thing is at 0 mean stress. Okay, so don't confuse. I didn't mention that this is 0 of the stress. It could be the negative. So what I'm saying is this ascent curve with the Basquine law always assume that this is 0, which is reverse loading conditions, like up and down. So tension, compression, tension, compression, something like that. So this endurance limit at 0 mean stress is important for you to double check. An endurance limit is generally defined as the cyclic stress level that enables infinite life in the materials. And again, the sigma F, or sometimes sigma F prime, whatever, this is the fractures or failure stress that is defined as, good catch, the ultimate stress of the materials. If you're considering more safety factors, then this kind of failure stress could be like much smaller. Like for example, if your safety factor is 2 and your materials can resist like 1,000 megapascals as the ultimate strengths of the material. Then if your safety factor is 2, then maybe your setup is like 500 instead of 1,000, something like that. But anyway, this is the informations of the total life. I really want to double check, like, do not confuse with this Basquine law with like similar equation, which is this. So as I mentioned, some people write A times NF power by B. Some people say this, or like some people actually write like B. But honestly, like these numbers doesn't make any differences because we're dealing with this like logarithmic scale of the graph. So as long as you understand the meaning of Basquine equation, then you will realize that this doesn't make any differences. So if you have this problem in final, then I will suggest, or I will mention what's the Basquine equation you have to use for solving the problem. And because of these values, maybe the cyclic loading could be number of cycles could be a little different, but it's not that different. I mean, it's actually pretty different, but I mean, I will like designate the Basquine equations in the final, so you don't have to worry about that. Okay, so let's go with the examples. I think you're pretty sure that this kind of derivations, just log, and then just delete it, and then get the B, and then you know B, then you can get this, and then if you have your ultimate tensile stress or ultimate stress, then you can switch these values to that. It's super easy.